So welcome everybody to Applied Mathematics and Statistics Colloquium, Friday afternoon. It is my pleasure to introduce Dr. Sarah Olson, visiting us from Worcester, I said it correctly, Worcester Polytechnic Institute. She studies lots of different things. I know her mostly for her work studying biological fluids and microorganism motility. She got her PhD from NC State in biomathematics in 2008. And from there, she went to do a postdoc at Tulane. And after that, she's been a professor, an assistant, and now associate professor at WPI. And I'm looking forward to hearing about her new work, her new recent work on cell motility.
So thanks, Karen, for the introduction. It's great to be here. I guess I'll preface this with, so this is some newer work, so I'd be very happy to take questions during the presentation. I don't necessarily need to make it to the end, so I will be very excited for questions, so please interrupt me. So I guess I'll start with, so the beginning of the presentation might seem a little bit odd, but I guess it's kind of how I got to the current problem, and I guess kind of a little more idea of how I'm viewing it. But so part of this work kind of started with some career funding from the NSF, and then most of this work is done with my current graduate student, Michael, and his funding now is through this SMART fellowship. Which is a great program that you should look into if you have never heard of it before. So this was our first experience applying. Okay, so I'm going to start off kind of fairly generic, and then eventually I'll get to some math, and again, please stop me with questions if you have them. But so I've been thinking about cell movement in different contexts for a number of years. I've done a lot with kind of microorganism motility and cell movement in different ways, but I guess the kind of unifying thing for all these cells is, in general, they're kind of generating forces, which allows them to wiggle and move in whatever environment they're in, if they're in a gel or a fluid. So I envision most of these things exhibiting forces. Once they exhibit have some forces, and they should bend or glide or crawl. And I've been concerned a lot with thinking about kind of what's the right force models, lots of details on that. And then, of course, if you're thinking about these cells moving, you have to think about why are they moving, chemical concentrations, different gradients of different environments, but kind of from biological perspectives, I was doing things with sperm motility, so it's very important for the sperm to actually move and find the egg. There's, wound healing, immune responses. So there's cells need to move, and they need to be guided there. So there's been lots of people thinking about kind of how do you model these things, and especially at different scales. So they're moving in terms of fluid flows, temperatures, chemicals. So I won't talk much. So normally I think about sperm a lot in different microorganisms, but this is just to say that in general, cells are moving. It may be just kind of in a very random way. They're generating forces where they move may be very random, or if it's guided by some chemical source, they might be kind of persistently moving in a certain direction or being guided in that motion. These are actually some different sperm trajectories for different experimental chemical conditions, and you can see basically that based on the chemical environment, how the thing is moving in space is very different. This is actually, so this is an experimental movie here, and that's a chemical concentration. It's a calcium fluorescence, which I think a lot about calcium signaling. But again, just to show you that cells, sperm cells, all different types of cells are kind of moving in different ways. And this really scattered plot here kind of shows with little arrows how the motility is changing at different time points. So I've been thinking a lot about kind of modeling these things from different perspectives. So the world I was primarily living in, or kind of the modeling approaches that I've been using previously, were thinking about kind of fluid structure interactions, or kind of modeling a background fluid flow, really thinking about modeling an entire surface or a structure. But we started to for a few different reasons, I started thinking about other things, but one issue we had was kind of scaling up to many cells. So here is some cilia moving with the little red, green, and blue markers are just kind of fluid particles, and we were looking at how they translate or how they move. And basically, it takes a very long time to compute these things, and we were thinking about, can we come up with some simpler representations? If I'm thinking about things moving in a fluid, so we're thinking a lot about kind of different ways to approach this, but what we have been doing is kind of solving some type of Stokes equations, and our force there was potentially from the swimmer or the cell exerting forces on the surrounding environment. But what we wanted to think a lot about was, how do we simplify the geometry, how do we simplify the forces, how do we simplify the interactions, and potentially to think about collective motion, but also to do a little bit more from kind of the analysis side to get to questions about kind of how long on average would it take this cell to reach a location, or what's the probability that it's going to be in a certain region at a certain point in time. And what we were doing is having to solve these problems and just solve them a bunch of times to kind of get a sense of that, and we didn't have any good analysis to do on that. So this is kind of the world I was living in, and then we were thinking about, okay, well, maybe we can, if we simplify our cell or our structure, is there a way to kind of go to a more agent-based model where instead of kind of solving all these complicated force balance equations, could we come up with some generic kind of governing rules to derive how this structure is moving on average, and then do some analysis or some simulation. So agent-based models, depending on where you're from, cellular automaton, you can think about it from a random block. They're all slightly different in notation, but they're all broadly, I broadly lump them together. There's definitely some subtleties between them. The basic idea is that they're rule-based, right? So if you have some idea that on average in experiments I see cells move in certain ways, then you can kind of bias the motion, or you can create a rule that says on average you're going to move left a certain amount in a certain given of time. So our agents could be cells, and these cells potentially could have different states. So some cells, when they're moving, they may be kind of quiescent or stationary for a period of time. Maybe they'll start moving again, so you can kind of classify them in different states. There may be interactions. You can do really complicated and interesting things, and you can kind of look at some emergent phenomena and interactions with the agent-based model, kind of similar to what we could do with our fluids model, but very different kind of approaches and governing equations. Okay. And in terms of these models, you can do more complicated things, but a lot of them are just thinking about a cell as a point. So I'm not doing some detailed representation of my cell or my structure, just thinking about a point and kind of how that point mass is moving in time. Okay, and I think about things mainly at the micro scale, but in terms of these modeling approaches, it's not limited to the micro scale. It really can be used at any scale that you're thinking about in terms of space and time. So agent-based models have grown in popularity for different kind of regimes. But I'm generally thinking about the micro scale. But yeah, so they're popular because you can handle complex interactions. If you have some rule or idea of how something behaves, you can implement that fairly easily. And you can think about, they're each maybe evaluating their own environment. They're kind of be autonomous. You can kind of have very heterogeneous and diverse agents. You can have different kind of states to describe movement. They could potentially adapt. They could have memory. I try not to deal with things with too much memory in my system because then it becomes more complicated. It could be, coupled to evolving continuous variables, right? So you can deal with kind of complex social processes or interactions and, build this kind of from a bottom-up approach. But in our group, so I had a few different students and I was working with a few different collaborators. So we were kind of trying to decide how best to kind of model some of the questions we were interested in for the different bio applications. And this is probably, I'll preface this, but this is how I view the world. So this could be very different depending on what area you're in. But we like kind of our fluid and our kind of PD models. We have very nice some analytic solutions, very nice established methods. There's kind of nice ways maybe to do sensitivity analysis, right? But some of these numerical schemes and kind of a continuum, the PDE or solving fluid equations can be complicated. There are definitely pros to agent-based models, but again, when you start dealing with large numbers, things can be complicated. There's issues with kind of how changing a parameter changes everything. There are people who do a lot of kind of understanding kind of more the statistical kind of parameter and sensitivity analysis, UQ on these types of models. But they're two different approaches, each depending on what you're interested in. One could be more appropriate than the other. So we were kind of going back and forth with our different cell motility models, and we liked each one for different applications that we were working on, but one of the things we were thinking about is, can we have some kind of hybrid thing? Can we think about an agent-based model and use it for some things and then push it to kind of a continuum version for certain cases where we wanted to use tools from PDEs that we were able to use, or things that we have handy to analyze these things. Okay, but more on, so the agent-based models that we're doing, you can think of them as kind of, so I have a cell, I'm thinking about it just as a point, and kind of random walk is just kind of the simplest thing, but just for illustration, and maybe, does everyone know what a random walk model is? Or, I'll see some, okay, so I don't know if I should go faster, but, so for this simple illustration, we're thinking about kind of points on a 1D lattice, assume equispaced in time and space. And then we can do things like think about, okay, so if I have a little cell or an agent at a particular point, what's the probability of being at this location at some new time point? Well, if I'm at that location, if I'm thinking about a random walk on a 1D line, if I want to be at this location, I either at the previous time step was one point to the left and I moved there, or it was one point to the right, and now I'm left and right. Anyways, I'm pointing to things that are hopefully left and right. So this is saying, right, if I was x minus delta, I was one point to the left, I moved right to get to x. If I was there and I decided not to move, and I stayed there for the next time step, or if I was one point to the right and then I moved left. So we can think about, for simple random walk case, we can kind of get to a nice kind of equation that's telling us something about, getting to something about the probability of being at that location. And these are kind of classical things. So if we assume that it's sufficiently smooth, we can kind of rewrite using Taylor series, and I think I added in some of that here. So, all right, so if you have P of x, t plus delta t, I can think about maybe rewriting P of x minus delta x t, kind of holding t fixed, doing multivariable Taylor series, plug in, and then you get something like this. So I just plugged in for the x minus delta x and then the x plus delta x, expanded a bit, and then things cancel, so that's the original thing there. So what ends up happening is when you expand it all out, some of the terms end up canceling, so those two terms cancel, those two terms cancel, and I can think about rearranging. So then I just have a P of x t here. If I move that over to the right-hand side, then I have a difference between the probabilities of t plus delta t and t, and then we can think about dividing through by delta t. Right, so you get this, you can think about dividing through by delta t, and then taking appropriate limits, and we can get back to some type of continuum framework. So if we rewrite limits as delta t, delta x go to 0 on proper assumptions of how they're approaching 0, we can arrive at kind of our continuum or our PD approximation known in the literature by various names. So we have a way to talk about kind of the rate of change of the probability of being at different locations in time. We can talk about kind of how you're advecting or moving more to the left or right, depending on what your probability is, and then kind of a diffusion term of how you're moving out in space. Okay. So we can do this, and you can get to kind of various things from there. We were doing, so this, oops, is it gonna play? So this is kind of we were doing some comparisons between a PDE approximation, or kind of our continuum approximation, and our little agent-based model. But I'll give you, so in the sperm motility context, I was thinking about, okay, if I have a bunch of sperm, if I think about when they're kind of swimming in the female reproductive tract, at some points they're kind of in these channels, so if I take a cross-section of it, so I was saying, so supposedly my cell or swimmer, if it hits this inner region, that's my egg target, so I just kind of had an absorbing boundary condition. So you can formulate things with boundary conditions. We were looking at the agent-based model, then we were looking at kind of the continuous approximation, and then we were trying to ask questions about, how long on average would it take to get to the egg or the target region. So you can kind of do some nice mathematics and computation and mix them together. So we started doing this, and this was, so I was working on this with my graduate student. And I'll say how we got sidetracked in a minute here, but so we could do these things with the random walk models, but again, just to kind of summarize, with most of these, kind of the random walk models in the literature are kind of a single cell in a single state. These simulations are really, nobody's interacting with each other, but I'm just running it, maybe I'm running it to 1 million realizations, so all the dots you see are kind of where things are going on 1 million realizations altogether. They're not interacting with each other. So we can do a single cell, single state. Most of the time, it's if you want to talk about a heterogeneous environment, you can think about kind of biasing your motion more to the left or the right at different time points. Most of the time we think about kind of them as time independent or kind of memoryless, some type of Markovian process, so it doesn't know or care where it was at previous time steps. So this is kind of the general literature, but there are kind of lots of different things in terms of random walks and random environments, bias-correlated random walks. So for the kind of microorganism applications, we were thinking about extending a few of these to talk about multiple states and kind of getting to more interesting heterogeneous environments. So that was kind of our initial goal when we started doing some of these things, to have multiple cell states with a time-dependent heterogeneous environment. But then we got sidetracked. So I had a biologist at UMass Medical, which is a little bit down the road from where we are at WPI in Worcester. And so he was talking to me, and he's like, I have all this great data, and I need someone to model it. And I said, okay. So he has these cells. They're different cancer cells, and he was applying different kind of drug treatments. And they were having trouble understanding some of the results, but these drug treatments, and this is one type of experiment, the purple is actually the viability, so it's still alive if you see a lot of purple. Less purple means the drug has killed most of the cells. But these experiments run for like 2 or 3 days, so there's actually a decent amount of cells moving. They're absorbing what could be a very non-homogeneous kind of drug concentration in here. And there's questions about, quite often cancer cells, there's different phenotypes, so there's kind of different cell states. So there was a lot going on, and we were thinking, could we use these kind of agent-based models and thinking about these cells moving, could we come up with some way to describe what was going on? So there were these experiments, cancer cells in here, and then we want to, so for the data, what they do is, they just kind of take images, and you have a sense of how much purple there is, and you have some sense of spatially where there's more live or dead cells, and by the intensity, you kind of know some idea of how many cells are still alive. But again, so there's cells moving, drug being absorbed. That drug, it's either absorbed, it's really binding to receptors on the cell surfaces, eventually upregulating some apoptotic pathway, but effectively, the more drug molecules it comes into contact with, it'll eventually die, most likely. Okay, so there's been some interesting things in the literature, but these are some other things. Sometimes they do it in a petri dish, sometimes they can actually have these like spheres of cells together. Sometimes they put these cancer cells in different gels or different mechanical environments. Here the green is live cells and the red are dead cells. So again, now we have potentially is this drug really getting to the center of the sphere? What's going on? And there's something, right, so the big motivation is there's this idea of fractional killing. So not all the cells will die, but some fraction of them will. The cancer cells are in these multiple phenotypes. The exposure to the drug could vary quite a bit in these kind of cell clusters. And then the reason I got really interested in this when this bio collaborator stopped by to show me all this data was kind of the mechanical environment. So what's really interesting is that, so breast cancer cells, when the breast cancer hasn't metastasized, it responds really well to certain treatments, but then if it's metastasized and gone to other parts of the body, it doesn't respond at all to the treatment. So they're hypothesizing that potentially it's the kind of the mechanical environment around the cells for those cancer cells somehow allows the drug to interact more or less with the cells. So there is a lot going on, but basically he came to us. I said, oh, maybe we can start modeling this, but we kind of had to start from scratch because I didn't have the right equations to go for it. So this is kind of the historical of why we started doing this. So what we wanted to do is try and come up kind of from the ground up, come up with some type of modeling framework. Maybe agent-based, maybe kind of continuum or PDEs. We wanted to think about, can we build some type of model? I want to be able to track cells moving. I want to track kind of the density of cells in space, kind of where are they in time. I want to also know how many particles of drug each of these cells have absorbed, or kind of how many are bound to receptors. And then kind of figure out tolerance. I want to be able to kind of capture cell movement and time to death. So, and then we're thinking about if you have more exposure to the drug, then you should eventually die in this simplified scenario. So we're really thinking about, can we, think about, average time spent in the live state? Can we match some of this data? And hypothetically, what they'd also like to know is, can we back out at the end of the day the parameters describing kind of how strongly these drugs, these particles of drug are interacting with these receptors? Okay. So in our agent-based model, I can think about a cell. I'm not dealing with cell interactions right now, so I just have a single cell. Potentially it's moving around. So our algorithm is kind of, I have a cell, it's moving around in space. It absorbs some chemical, or the drug particles are binding to the receptors or interacting with the cell. And that's going to kind of accumulate in time. The more particles it interacts with, the closer it is to cell death. Above some threshold, I'm going to say, well, then that's toxic to the cell. You've kind of upregulated these different apoptotic pathways, and therefore the cell should be dying. Okay, so we did with this with an agent-based model. So let me describe the setup. So here we're thinking about, say, 100,000 realizations. So we do this, 10,000, 1,000, a bunch of different times. Every time we're going to start the cell. So this is just a 1D simulation. So here I just have just a spatial 1D kind of grid right now. I'm effectively doing 100,000 or some amount of simulations. And this is saying, and then I'm kind of collapsing it all onto this and then showing you basically the 100,000 realizations simultaneously. And in this toy model, we're thinking about, okay, maybe the cells are always starting kind of in the center of the region where the drug is. So the region where the drug is just this gray bar. And then, it may be moving in and out of the region with the drug. So the longer it stays in the time with the drug, then it should be being exposed to more kind of particles of the drug, which then should be causing it to die eventually. Okay, so there's this chemical concentration. It's just, kind of set this characteristics function. It's just kind of set in this one region, and then it's zero outside it. We're thinking about a cell. A cell may be binned at a certain point, but we're thinking about kind of what the concentration is in that kind of bin or where it is, and saying it's going to absorb some fraction of that. And we use some step sizes, and let me start the... Okay. So I start with all the cells in the middle. They're going to undergo just a random walk, so it's equal probability of moving left or right, but then at each moment in time, they're interacting with these drug particles, and potentially, once it's interacted with enough particles of the drug, they're dying. So what you see is we start with all the cells in the middle. We have a really high density of cells right in the middle. And then as they move in space, the amount of cells that are still alive is going to decrease. And then we run the simulation to some time points. So we have some cells that have kind of moved out of this region with drugs, so they're still alive. Very few that are left alive here, and then, it's only run for a finite period of time, so they haven't moved that far out of the domain. Okay, so step sizes, and then if we actually look at kind of what's going on in 1D, I can actually plot this as well for, so this is time. The color here is kind of the density or proportion of cells that are still alive. So at the beginning, everybody's alive, which is the yellow here, and then they start moving left or right, but those that kind of stay in the middle are dying, so it kind of goes to, yes, please.
Is the time in seconds, or is that just like a general?
Sure, seconds. Yeah, it's kind of, it's a toy model right now, so you can think of everything kind of non-dimensional, but so yes, when we go to units, it would most likely be seconds, or cells usually move like a few microns a second. So yeah, so if you think about this as kind of a scale of microns and seconds, is probably fairly realistic. Well, maybe they wouldn't have died in seconds. It would be a little bit longer, but okay. Any other questions before? Okay. So okay, fine, we could simulate this, but we were actually really interested in whether or not there was some nice kind of partial differential equation or some governing equation that we could think about deriving, right? So for just a random walk with moving left or right, we can come up with kind of a nice PDE for it. So we were wondering, can we do this here? Where now kind of the complication is, instead of just moving left or right, you're also absorbing or kind of interacting with a cumulative number of these drug particles. So instead of just tracking, whether you're moving left or right or kind of your spatial locations, we are also going to think about kind of continuously modeling the number of particles of drug that you've cumulatively interacted with in time. So instead of just talking about, just space and time, now we're thinking about a continuous function of space, time, and kind of this cumulative drug effect, which could be going from, 0 to, positive real values, right? Okay, so we're assuming we're on some domain. We were fiddling around with things, so we played with kind of a finite fixed domain, and then we moved to kind of a free space case, but suppose we're on some domain. A cell, if a cell is at a given location, it's going to absorb or interact with some of these drug particles. We're assuming that that's kind of in a region right around your cell. And we're going to assume that there is some kind of chemical concentration. So there's so many moles or kind of particles of drug for a given spatial region. And then some fraction of those are going to, at each spatial region, some fraction of those are going to interact with the cell and potentially accumulate to cause it to die. So C is going to be the amount of chemical, and then there's going to be some threshold where above that, effectively the cell should die because it's been exposed to enough chemical. Okay, so we have probabilities moving left and right, and we can kind of go in the same way that we proceeded for the other stuff. So here I can think about, I guess not probability, I meant to change that. So U, I guess, maybe a better way to describe it, of X, T, and C. So U of X, T, and C is really the density of cells in the total population of cells. And we're thinking about it, right, being a function of space, time, and some type of chemical concentration. And before, when we did it for just moving left and right, we were thinking about, okay, what's the probability or kind of the proportion of cells that are at a space at some new time point. So we're kind of thinking about, okay, this is the kind of density of cells that are at this location, at this time point, given that you've already absorbed some, or you've already interacted with the drug particles there. So I'm thinking about some continuous function to talk about the density of cells that are at this location, at this time point, that have already absorbed or interacted with this many particles of drug.
But it looks like B depends on the T.
Kind of, yeah, so this is one of our struggles. So in the current setup, we're assuming we have a fixed concentration of drugs. So I have so many particles per each region of space. And we're assuming that in a given time interval, you just absorb some fraction of that. So I have kind of this alpha here is a rate or kind of a 1 over time. This is a concentration or kind of particles per volume. And then because this doesn't depend on time, when I integrate it out, it has rates. So you end up getting, if you just did some integral rule, you pick up a delta t, but then it's just a function of x times some delta t when you do that integral. So you pick up a delta t, but it doesn't, the amount you absorb depends on where you are. And if it's that chemical concentration at that time point, it doesn't, if it's that chemical concentration at that particular spatial point, it doesn't, no matter what time, if you're at that spot, you're still going to absorb the same amount. Does that make sense?
The alpha is a rate, so the alpha has inverse time.
Yeah,
so it doesn't have any units of time, but it does have a step size to absorption rate kind of scale.
Scaling, yes.
Is that correct?
Correct. Yeah, because this is 1 over time, and that's time, so those are canceling. And this is what particles per some length, area, volume, whatever dimension you're in, and that cancels with that. So at the end of the day, B of x, is going to be effectively kind of the number of particles that you've absorbed at that spatial location that you're at. Please.
So if that changed in time, then that integral, we'd have to care about that, right? Because right now we could just formulate it as 0 to delta t.
Yes. So we've also played around with the more complicated case of actually having it depend on time. But in the simple one I'm showing you, so I'm not sure exactly how to deal with it, but so right now we're assuming, we're kind of just trying to say, let's try and keep track of, so it's not really a memory thing, but you are having this extra continuous variable of everybody coming into contact with a different number of particles. What ends up happening, right, so it's kind of multivariable, you have to do the Taylor series appropriately, but we can do the same thing and say, well, if I'm at this spot x, I was either left of it or right of it. If I have some C plus some new amount of particles that I've interacted with, then I must have had C at the time point before. There's some extra subtleties of the amount of particles that you would have absorbed potentially is going to depend on whether you came for left or right. But okay, so if we do this, we can do the same thing as before, expand this Taylor series, try and cancel some things out, and what we end up getting is kind of the same type of, so this, it's just kind of a diffusion term, so it's talking about how my density of cells is kind of spreading out in space. This is talking about kind of my density of cells potentially having a bias to move to the left or the right, kind of an advection term. And the weird term is this one. So there's this extra kind of advection in this extra variable where if you've been exposed to more chemical, you're going to kind of advect or get moved into the density of cells is going to change for the different cases. And I'm probably not saying that very nicely, but okay. So what we end up getting is this type of PDE where we're talking about, so my function U here is the density of cells that is a continuous function of space-time and the amount of particles of drug that you've been exposed to. Okay, and right now, so we've been going back and forth, but for reasons I'll explain later, right now we're just going to say, okay, suppose I'm in free space, so I should have that the density of my cells is going to 0 after boundaries, and we're going to start with some point source of cells at time 0. Questions?
It looked like a few minutes ago, right? That I think we agreed that B of X is actually proportional to delta T.
So the
Because I'm just wondering, I mean, that might help you, right? B of X is something like delta T.
Because this is, right, so this is 1 over time and this is time, then I don't get that time unit, but when I'm rewriting things to get this du dt, I divide by delta t, so I end up picking this over delta t here. But this is, so this is particles, this is some, density or proportion of the density with cells.
It looks to me like B of X is equal to delta T times a function of X.
Yes, and alpha has units 1 over time.
So you worry about the terminology. I'm sure you saw,
Maybe. I might convince you later, but you may still have questions.
So I'm trying to understand, can I just ask
Yeah,
one question?
please.
So if I'm a density of cells in one region and I absorb some particles and then I move to another region, do I know that I've already absorbed those particles from over here?
Yes.
Or is it just that at every point in space there's just absorption? If it's just in space, then it feels like there's just this constant absorption at that point in space. But
that point in the
it's not being absorbed.
The space
tracked, but it is.
It's being absorbed. It's accumulating. So I guess based on previous conversations. So when we're doing the age of this model, it's accumulating. So it's the kind of the cumulative number of drug particles that have bound to your receptors and have basically primed you to eventually die.
So then the amount of particles you've absorbed, if you're one cell that has absorbed 10 particles, and then you move to a region where there's 10 cells that altogether have only absorbed 1 particle, then you're now 11 cells that have absorbed. Shoot, what did I say? I'm trying to figure out how.
Because
we can talk later.
Yeah, so I mean, it's a density. You have some approximation of where things are moving and you're accumulating. And we did try and do it in a discrete way to mark out chains and things, but it got too complicated, yes.
So then it also kind of seems that we're assuming that the density of the drug stays relatively constant, or that the drug doesn't move, I should say.
It's fixed in space.
And it only changes based on cells absorbing.
So we are keeping a fixed concentration in space. The cells are absorbing or it's binding to its receptor, but we're not removing that from the underlying concentration field. But at each point in space, some fraction of the drug particles that are in that kind of area or volume may bind to a receptor and affect the cell's behavior to change its state and die.
Is that fraction assumed to be small?
The fraction of cells that die, or the fraction
of drug absorbed by the cell in the site.
So at the moment, yes. Yeah, I mean, there's some very low probability of it actually binding, and in most of these experiments, it's pretty high concentrations that they're putting into these. Okay. So we can come up with some type of PDE. We can do this for 1D, which is what I kind of described. If we assume a constant kind of spatial step in each of the other directions, we can effectively do it in higher dimensions. I can do kind of it in 2D or 3D. Now your spatial coordinates is x, y, x, y, and z, but the amount you absorb is going to be based on that concentration at that particular point in space, so it's just still a function of that spatial point. Okay. So what we were we were intrigued by this thing, this equation, and if anybody has seen kind of terms like this, I would be happy to chat with you afterwards. We first tried to do some really rough finite difference methods just as a proof of concept. We found that they matched nicely, but they were really finicky with how we were discretizing our kind of particles that the drug, the number of particles that have interacted with the cell for that C variable. So we decided to, which is why we moved to free space, to kind of work with a few things, but we wanted to know, does it match with the agent-based model? It did in some initial simulations, but it didn't kind of converge nicely. But we wanted to make sure that for this type of problem that we actually have a unique solution, that we have some stability. So we thought about kind of starting off with some energy arguments, trying to think about, can we say that we have a unique solution? Can we do anything with this kind of equation that we have here? So to use an energy argument, we want to say effectively, we want to look at this integral, kind of like a kinetic energy, and then we want to look at the derivative of it, and we want to show that it's decreasing to show that we have kind of stability. Okay.
How do we think of the variable C? Or how do you think of the variable C? Do you have a kind of...
So this is my
It's not a spatial variable, right? It's not a time variable. So what is it?
It's this number of particles that you've interacted with, and potentially it's going from 0 to positive infinity, hypothetically.
It's an independent variable.
I know this is.
We've been having these discussions all day.
It should be infinite because it's some critical value to
Yeah,
cell.
yeah, but hypothetically, it could be a very large amount of...
Arbitrarily large.
It could be arbitrarily large. Yeah, no, I don't, if you don't say that, how
No idea. I'm quite honest about that. But you've written it as an independent variable.
Yes.
Yes. So we were trying to do some things with kind of classic energy arguments, and I should be done in by 50, is that?
Yeah.
Okay, sure. I went too slow, but that's okay. So we did some kind of classical things with energy arguments. You can break things up. You can kind of, you have this U-squared thing. We can look at the derivative of it, Leibniz rule, with some assumptions. We can take derivatives inside. We can think about, if we're in the free space case, knowing that hopefully the density is going to be kind of finite, or for finite t, that it's going to be approximately 0 infinity. We can get rid of some of these integral pieces. We can simplify things a decent amount, and we can effectively get to something. We also, it's on this slide or the next one, there's also, it's not here, okay. So we can say how that the energy is decreasing in time. So we're happy, okay, we have some type of equation that maybe we can be guaranteed that we can have stability, and also when you do this energy argument, we can then think about, do we have uniqueness? So you can say, well, if I have two solutions, U1 and U2, I can come up with some linear combination, plug that in, and via the energy argument, you can also say that, well, I have uniqueness, they must be the same thing. So we also didn't have a nice direct analytical solution. We tried some really simple finite difference methods. Things weren't converging nicely, so we ended up going back to kind of our free space case. For standard diffusion, we have fundamental solutions and kind of Green's functions and things that we can use. We thought about, because also we didn't know how to deal with this C, so we thought about kind of breaking it up into a piece that, assuming C is fixed, can we break it up kind of like separation of variables? Can we think about breaking up kind of our spatial time thing from our C? So we tried to break that up. We did kind of we did some separation of variables, used our Green's functions. I'm going to skip over this, but we do kind of a method of characteristics to deal with that. And effectively, we kind of came up with an algorithm where we have our Green's functions, and we're kind of dealing with the previous time step, and then we're doing some method of characteristics to get there. So in the interest of time, I just blew through the numerical method. But we should have stability. We have some type of algorithm, but I guess I want to get to the results. So this is kind of back to a 1D case. So we have an agent-based model here, and then kind of our continuous approximation with the PDE. And again, we're starting, I think, with a point source. So in the agent-based model, I have, say, 100,000 or a million simulations. I start with them all here. They start moving and they start dying. These are kind of the contours to show you what's going on. And then we can do the same thing with the PDE. We just start with a point source, use fundamental solutions, and have this weird kind of action thing for the number of particles you've been exposed to, and we can get fairly good agreement. Okay, and then here also, what we do is we think about it continuous and kind of the number of particles that you've absorbed. So we have kind of the total density of cells. But what we're going to say is that if you've absorbed or interacted with some thresholds of CC, if it's less than that, you're alive. If you're above that, then you've kind of went into the death stage. So we can look in time, over our entire domain, kind of what's the proportion of cells that are in the live state, and kind of match it up with our agent-based model and the PDE framework. And then we can do some fancier things. So we can think about also deriving these things, kind of mean first passage time, mean occupancy time, talking about kind of flux in and out of this light and dead state. The interesting thing as well is so this is different drug absorption curves. So these are different drug absorption curves. These curves that are kind of going down, this is talking about the fraction of the cells that are the total amount, proportion of cells that are still alive in time, so they start dying across the domain. And then these dashed lines, I think, are kind of the mean occupancy time that a cell is in the live state. And we can do some curve fitting. But what we found out is that if we do this, the nice thing is if we know something about mean occupancy time, so if the experimental data could say how long on average cells are staying in the live state from kind of some of the imaging with some nonlinearly square solvers and some things, we can hypothetically back out the absorption parameter if we know what the concentration profile is, but we don't always know that. Other things that we were curious about, so these don't match up as well, but we haven't done a ton to look at these, but we were thinking about right now, what I showed you was a single cell. It had an equal probability of moving left and right, but now, and kind of always with the same spatial step. The idea is that if a cell is maybe getting ready to die, maybe it shouldn't be moving as fast, so we can think about trying to bias the motion based on how much chemical or how many drug particles it's interacted with. Then we can do things like, well, does this work in 2D? So my student was having a little bit of fun, but he started, so this is kind of the concentration profile, so high drug concentration is in these yellow regions. So what he does is he starts a point source of a large number of cells kind of right here. So those cells that move into the high concentration region are dying. The ones, you see the proportion of live cells, and they're kind of moving into these regions here where there's no drug, and that's where they're still living. And again, we can match the kind of continuum approximation with the PDE we derived. So we're still not quite sure how to talk about this differential equation, but we think we maybe have an okay solution for it. But everything I showed you was basically a single cell state, but then we can kind of cut off based on this continuous variable. We say, okay, if you're in this range, we're classifying you as a particular state. We really wanted to work with additional cell states. I really don't want a constant chemical concentration, but then that's going to be time varying and spatially varying. Biasing the motion, thinking about cell interactions and porosity. So we have been doing some work to think about cells in these different kind of scaffolds and tried to come up with some PDEs. We're having some okay agreement. So here we have kind of a way to bias the movement based on kind of different obstructions. And then we can also do different things like multiple cells and obstructions and come up with some governing equations. But I guess I'll finish off by saying, so we're working towards, our ultimate goal is really understanding cell motility, but being able to couple cell motility with these kind of varying drug concentrations, with the ultimate goal of maybe actually being able to match some of the experimental data one day, and being able to kind of make some predictions about what they're seeing in terms of these different cell survivals and these different experiments. Okay, I think that's it.
When you showed the movie that your student
Yes. The 2D movie?
so you've got X and Y on the left, and this is the movie, so this is the function of time. Where did C go?
His C's not here. So
So have you been,
So what you're
so
seeing.
that's not the plot of you, right?
So this is not a plot of you. This is a plot of you, and at each time point, we're plotting the proportion that is in between 0 and that critical amount. So there is a fraction.
So it's like an integral with respect to C.
Yeah, I'm doing an integral with respect to C of 0 to that critical threshold, because U is basically all the cells, and then when I'm, so I probably didn't, I probably did not specify. So when we're doing this movie, what you're seeing is we've already kind of taken off the dead cells, so that way you can actually see how they're kind of still staying alive in the regions of blinking.
So, can you integrate PE with respect to C?
That's exactly what I was going to say.
Sorry.
No, that makes perfect sense. Because what's your boundary condition of U when C is 0?
No. Wait, so...
What is your boundary? Sorry.
I said no, it's...
Yeah, it's okay.
I thought you said, is it 0?
No,
Sorry.
it's not. You said it's not.
I don't have a boundary condition on
C.
C.
In the C variable. Because what I think Paul was just going to say is you take the PD you have and you average in C, and that goes through each term, except the adaptive term in C, but then from a third calculus tells you that that's U at infinity in C minus U at 0 in C. And that gives you effectively an average PDE for what you're actually computing here, right? Does that make sense what I'm saying? I'm asking both of you that question.
Well, that's more or less what I was thinking.
Yeah.
But you must have thought this as well, right? Since you are trying to integrate.
So I think we thought about it, but then because we want a time-dependent, and we want to couple that weird advective term in that particle number. Because we want to couple it to another PDE, I think we were thinking that in the long run wasn't going to help us in the long run, but it might be helpful here for some match.
So then, I know you discussed how you guys are kind of looking into how it changes based on the mechanics around it. So like it has certain fluids or function of body, I guess. So then, do you have anything like interesting that you've seen about that so far that might indicate?
So we're still trying to figure out how to incorporate that. So these gels sometimes have these they have empty pore spaces where cells can move, and then it's kind of very dense network of proteins or fibers. So we thought about, okay, well, maybe we can bias the motion based on knowing kind of that structure. Maybe we can come up with some function to govern it. But no, we don't have a good way of doing that at the moment. And for the mechanical stuff, I was really thinking that the mechanical should somehow feed into kind of the drug absorption or rate. So they hypothesized that maybe they can't actually bind on, or that the cell is already maybe the cell is already bound to some of the gel or some of the proteins. So there's different hypotheses about why it's working, which we could change a few things in here, but we haven't gotten there yet. We got sidetracked with trying to make sure that we can even understand the first equation and then try and simulate that.
This is a hard problem, though. I mean, it's the reason why I like in our plotting model that our platelets don't come off of the clot and react is because how do you track the chemical reactions on moving densities? It's a really hard problem. So I kind of just put it together because I was thinking, why wouldn't you just compare it to like an ADR equation? But it's because you have to track those densities that are reacting as they're moving, and they have to sort of track that information with them as they move.
Yes.
Like it works. It's awesome. I like it.
What sort of conditions if we impose on you regarded as a function of C? somehow initial conditions or something.
So what? Okay, so
You have an initial condition, right?
So-
the actual time.
So in order to say energy stable and all these things, I have to say that effectively, I say that basically when I start the density, everybody's x equals 0 at time 0. So for the stability and energy of the numerical method, I have to, all I say is that basically the entire density of cells has 0 particles at time 0. And I don't know, so part of the reason we did some of this energy stability was like, do we need some other assumptions or conditions? And then our other thing was we had thought about putting a boundary condition to say that instead of keeping a continuous thing, we thought about chopping it up and doing harmonic things. Then we thought about imposing a hard condition on U to say that at this threshold, U goes to 0. So then U is just the actual live cells, but then we had some issues with that kind of thinking. But there may need to be some additional conditions, but we haven't figured anything out.
So let's thank Sarah for sharing her thought off the class